Testing. 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 Okay, we're live on there. See if the volume works. Testing. 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 Okay, I think we're good. Welcome to another stream. Today we're going into the NERF world. We're going to be looking at Language Embedded Radiance Fields. This is a paper where someone basically combined a NERF, which is a neural radiance field, and then they added language to it, probably through the use of clip. Yep, so clip embeddings. Optimizes a dense, multi-scale 3D field by volume rendering clip embeddings. Along training arrays, supervising these embeddings with multi-scale clip features across multi-view training images. After optimization, the LERF can extract 3D relevancy maps for language queries interactively in real time. So 3D relevancy maps, that's what you're seeing here. Basically, within specific areas of the NERF, you can convert this text NERF gun and then see which parts of the NERF correspond the most strongly to that natural text query. It's a really cool application. LERF enables pixel-aligned queries of the distilled 3D clip without relying on region proposal, masks, or fine-tuning. I mean, without relying on fine-tuning, the fine-tuning was already done. At the end of the day, someone had to train clip, supporting long-tail open vocabulary queries hierarchically across the volume. So the volume here is the 3D space. So NERFs. In any kind of neural rendering, really what they're doing is they're defining a field, right? Field which has volumes at any, or which has any value at some point in a volume where the 3D comes in. So very beautiful visualizations as well. This is like a really nice paper website. Really lots of effort went into the actual stuff here, and there's a lot of really cool applications here. Yeah, I mean, this is super nice. But it's important to realize this isn't something that runs in real time. You know, if you wanted to use this, you would first have to create a NERF of this scene. And in order to create a NERF of this kind of entryway, for example, you would need to have hundreds of images of this entryway. So it's not like this is something you could use to find the bread at the grocery store. It already needs to have a trained NERF to do that. This here was actually one of the reasons why I decided to do this paper, is just because the figures here are super nice, very clean figures, very well done. Look at this. Look at this beautiful like feature pyramid here. You know, I'm a sucker for very well done paper figures. We pre-compute an image pyramid of clip features for each training view. Then each sampled ray during optimization is supervised by interpolating the clip embedding with this pyramid. So much work is based off this clip embedding. And honestly, clip is quite old at this point. I wonder what the successor of clip will be, because inevitably there will be one. Clip is super popular because of its open source nature. Or not open source, but at least it's released. But I feel like it's been a while now, so there has to be a better one internally to companies like Google and Meta and OpenAI. So hopefully they release it and we can see all these different clip-based applications. go to the next level as well. Dino regularization. Inspired by distilled feature fields, we use Dino features to regularize clip features. This is the meta paper, right? No, this is not the meta paper. Okay, this is deep VIT features. So this is vision transformers and then visual descriptors, pair of images, point correspondences. Okay. This is clustering, deep VIT, co-segment common objects. This might actually even be the same group of people. Shir, Yasi, Shai, and Ali. Are there any common people within that? Her, Ken, Glue, Matt. It's interesting. Okay, it's not. I'm looking here at the names, right? And sometimes whenever you see papers that use a different paper, it's oftentimes the same author has just, and that's just the new paper. This is a different set of authors. LERF and Chachi BT. Okay, very cool. Natural language interaction could allow LLMs to interrogate the 3D world. We show an illustrative example where Chachi BT provides a large queries of objects to look for to clean a coffee spill. I do agree with this, and I think that the 3D world, the problem with this is that you need the 3D world mapped. So you would need to basically constantly be taking pictures of the 3D world and maintaining a neural representation of the volume of your house or whatever it is at all times, which isn't necessarily impossible. I think that you could imagine how if people are wearing VR headsets that are constantly kind of looking everywhere, then constantly having an up-to-date map would be possible and fine. All right, NERFs will be integrated into the popular research code-based NERF Studio. This is different from Instant NGP. I think there's a couple different GitHub repos that are starting to become popular for NERFs. There's this one here, NERF Studio, but then there's also Instant NGP. NGP. Yeah, this one. This is another really popular one. This one is actually NVIDIA maintained, I'm pretty sure, but I don't think it might not be MIT licensed. That might be the issue. Yeah, so let's look at the license on this. Yeah, so this is the problem. It's NVIDIA Corporation, copyright. So I believe that's not the case with NERF Studio. That is not NERF Studio Apache license, which is what you want. So if you guys are doing any kind of startup or any kind of project that you want to maybe consider making into a product or consider doing your own thing with, definitely don't use the Instant NGP. Use this NERF Studio. Apache 2 license way better than the whatever obscure license the NERF Studio has. Citation. All right, cool. So let's get to it. This paper seems awesome, and I'm excited to dive into this. All right, so we got LERF, Language Embedded Radiance Fields. UC Berkeley. I think Ken Goldberg, this is actually the guy who did a bunch of robot manipulation stuff, if I'm not mistaken. Ken Goldberg, Berkeley. Yeah. Did forget the name of it, but there was like a series of papers where they were basically grabbing weird 3D printed objects with robot hands. So kind of a weird pivot, I guess, but hey, I'm also a robotics person that now just kind of moved away from robots, so I totally understand. Robots are hard. AI is much more easy. a nice big figure here. We have the volume of 3D space, this square that encloses a radiance field, right? The way that NERFs work, they have a neural network which parameterizes a field, which basically means that you give the neural network any point in space and it'll tell you what the color of that point in space is. And basically what they're going to be doing here is they're going to be adding a language embedding to that point in space as well, probably. LERF grounds clip representations in a dense multi-scale 3D field. LERF can be reconstructed by a handheld phone capture within 45 minutes. Yeah, so 45 minutes to scan this kitchen. It seems a little bit intense, but I'm sure over time that'll go down. We can render dense relevancy maps given textual queries interactively in real time. Okay. LERF enables a broad range of concepts to be queried via a natural concept from abstract queries to long-tail objects such as Waldo. Even reading text like boops on the mug. That's pretty cool. For each prompt, an RGB image and relevancy map are rendered, focusing on the location with maximum relevancy activation. Yeah, I wonder how they do this. This is another interesting part, right? So this field is kind of infinitely dense, right? Like the neural network that defines what the field looks like in here, you could query it at kind of any point in this volume. So the amount of, like, if you have some specific query such as yellow or electricity or Waldo, you're doing some kind of similarity search, right? And doing that quickly and efficiently is you're gonna have to do something, especially if they say here interactively in real time. I wonder if they're doing some kind of octree or being clever about kind of searching through this 3D volume of language embeddings in order to find the one that most closely matches the user query. So there's a lot of different tricks that they probably created that I'm interested in seeing how they did. Right. Humans describe the physical world using natural language to specify 3D locations based on a vast range of properties: visual appearance, semantics, abstract associations, or actionable affordances. Okay. In this work, we propose language embedded radiance fields, LERFs, method for grounding language embeddings from off-the-shelf models like CLIP into NERF. This is basically the TLDR of the entire paper, CLIP into NERF. LERF learns a dense multi-scale language field inside NERF by volume rendering CLIP embeddings along training rays, supervising these embeddings across training views to provide a multi-view consistency and smooth the underlying language field. Yeah, so while they're training the NERF, they probably feed all the kind of intermediate frames into CLIP and then get text from that. After optimization, can extract 3D relevancy maps for a broad range, which has potential use cases in robotics, understanding vision language models, and interacting with 3D scenes. LERF enables pixel-aligned zero-shot queries on the distilled CLIP embeddings without relying on region proposal or masks. This is here. I feel like most people in computer vision, right? Maybe not most people, maybe I'm more alone in this, but I've always felt that bounding boxes and masks, segmentation are just not great, right? It's not, it feels like an intermediate solution, right? Ultimately, we want scene understanding, right? For things like robots and VR and AR, we need this kind of 3D understanding of the world. But I always thought that having bounding boxes and segmentations and masks, that's just doesn't seem like the final solution, right? It seems like kind of a temporary abstraction that we've created that allows the creation of supervised learning systems. But now more and more, we're seeing supervised deep learning kind of fall out of favor. And I feel like bounding boxes and segmentation masks are going to kind of go away. And maybe this is what the future looks like, right? You have these radiance fields parameterized by neural networks, and rather than saying, hey, this box on this 2D image represents the wine bottle, it's this region of 3D space within my NERF volume represents the wine bottle. The project website at lerf.io. Yeah, I wonder, do they have a little GitHub? No. The code literally just links to the project itself. Oh, okay, no. Integrate it into NERF Studio. Wonder if they have a pull request. Let's look is PR, and then let's do LERF. Nope. Language. Nope. There still isn't even a PR for this. Maybe they just didn't use the name language or LERF, but okay, let's get to an introduction. This is probably going to be a summary of NERFs. We have neural radiance fields have emerged as a powerful technique for capturing photorealistic digital representations of intricate real-world scenes. The immediate output is nothing but a colorful density field. Now they just define a field in a volume. Natural language is an intuitive interface. It's the interface of the future. I think we've realized with LLMs that we're going to move away from GUIs, right? Like graphical user interfaces and point and click, and we're going to move into a world where you interact with technology using natural language, and I think this represents a important step in that direction. Consider the capture of a kitchen in figure 1. Imagine being able to navigate this kitchen by asking where the utensils are, or more specifically for a tool that could use for stirring. And even your favorite mug, all through the comfort and familiarity of everyday conversation. Right there. Requires not only the capacity to handle natural language input queries, but also the ability to incorporate semantics at multiple scales and relate to long tail and abstract concepts. Okay, so here they're kind of teasing the multiple scale here. So did see that they have this kind of pyramid concept. So this is something that's been around in computer vision for a long time, but the idea of having kind of the same data but represented at different resolutions, different scales. Sometimes these are called feature pyramids because usually the stuff, the meat of each layer of the pyramid is features, right? But they're going to probably use this concept we see here for different scales of the same image. Here we have an image of Waldo. That's what they're teasing there with the multiple scales. We propose language embedded radiance fields, a novel approach that grounds languages within NERF by optimizing embeddings for an off-the-shelf vision language model like CLIP into 3D scenes. LERF uses CLIP directly without the need for fine-tuning through datasets like COCO or reliance on mask and region proposals. Okay, so there's a little bit of kind of misdirection here. I feel like the CLIP itself has very likely seen all the data in COCO, so you can't say, hey, we're using CLIP, but hey, we're not using COCO, because I'm pretty sure CLIP uses COCO or was trained on COCO. So something to keep in mind there. Because LERF preserves the integrity of CLIP embeddings at multiple scales, it is able to handle a broad range of language queries. Construct LERF by optimizing a language field jointly with the NERF. Okay, so this is actually how they're doing it. I wonder if they use the same model or whether they're going to use two different models, right? Are they going to build a radiance field, a neural net that basically just outputs color and opacity and radiance and stuff like that? Or are they going to have two neural nets, one that outputs the language field and one that outputs the radiance field, the color, the visual information? Takes both position and physical scale as input and outputs a single clip vector. Takes both position and physical scale as input and outputs a single clip vector. Okay. Field is supervised using a multi-scale feature pyramid. Multi-scale feature pyramid that contains clip embeddings generated from image crops of training views. This allows clip encoder to capture different scales of image context, thus associating the same 3D location with distinct language embeddings at different scales, e.g. utensil versus wooden spoon. Language field can be queried at arbitrary scales during test time to obtain 3D relevancy maps. Okay, so this is probably how they're going to be doing the actual search problem, right? So when you have some kind of query, such as Waldo, right? You need to, at some point, you're going to have to do some kind of similarity search over this entire volume of space. So that could take forever, right? Especially if this volume of space is very dense and has a lot of different stuff in it. So it sounds like that's where the kind of multiple resolutions, this multi-scale aspect is going to come into use, where first you'll likely be querying it at the coarsest resolution, right, at the highest scale, and then choose a specific voxel within that, and then kind of go deeper and deeper, very similar to an octree. If you guys have ever seen this, octrees are a way of storing or kind of breaking up 3D space into little smaller 3D spaces that is efficient and very easy to search through. So it's all about basically creating this tree. This is a good example of increasingly smaller and smaller and more finer and finer resolution voxels within a larger volume of space. And they're very popular because they're very fast. They have a lot of kind of theoretical guarantees, and right, being a graph, you can kind of predict how long it's going to take you to get stuff and how much information you're going to be able to store and so on. To regularize the optimized language field, self-supervised dyno features are also incorporated through a shared bottleneck. Okay, this seems a little bit more interesting here. Some additional regularization that's happening using dyno features. As we extract clip embeddings from multiple views over multiple scales, the relevancy map of text queries obtained through our 3D clip are more localized compared to those obtained via 2D clip embeddings. They're also 3D consistent, enabling queries directly into 3D fields. Yeah, so they're going to extract the clip embeddings from multiple views over multiple scales. Right, so clip itself is not 3D. Clip takes as input 2D images. So at some point, they're going to have to convert the 3D information that is being stored in this NERF volume into 2D images that they can get clip embeddings from. So that's why they're going to be doing these multiple views of the same place. LERF can be trained without significantly slowing down the base NERF implementation. On completion of the training process, LERF allows for the generation of 3D relevancy maps for a wide range of language prompts in a real time. We evaluate the capabilities of LERF on a set of handheld captured in the wild scenes and find it can localize both fine-grained queries related to highly specific parts of geometry or abstract queries related to multiple objects. LERF produces a view-consistent relevancy map in 3D across a wide range of queries and scenes, which are best viewed in videos on our website. We also provide quantitative evaluations against popular open vocab detectors. Okay, so these are different detection models here. You have LSEG, OWL VIT. By distilling LSEG features into 3D and querying LVIT from rendered novel views. Our results suggest that features in 3D from LERF can localize a wide variety of queries across in the wild scenes. The zero-shot capabilities of LERF leads to potential use cases in robotics, analyzing vision language models, and interacting with 3D scenes. Cool, I like that. Two related work. This is going to talk about different things. We have open vocabulary object detection. So object detection up until now usually basically means finding bounding boxes for specific things in a 2D image. Open vocabulary refers to the fact that the categories of objects that you're detecting aren't limited to a specific set of categories upon which the original model was trained. Right, so something like Coco, for example, this one here. This is a data set that was released quite some time now, but there's, I think, like 1,000 different categories, right? And in that case, Coco is object detection, but it's not, it's a closed vocabulary, right? There's a limited set of categories that you could use in Coco. Open vocabulary object detection is about object detection without a closed vocabulary, right? You can basically put anything in there. These lie on a spectrum from purely zero shot again. Well, not again, right? I shouldn't assume that you guys watch all my videos, but zero shot basically means without fine tuning, trying a model on a new task without fine tuning it on that task. LSEG trains a 2D image encoder on labeled segmentation datasets, which outputs pixel-wise embeddings that best match the clip text embedding of the segmentation label at that given pixel. Chris and ClipSeg. Okay, you see how LSEG uses clip. Chris and ClipSeg also use clip. Right, so all of these open vocabulary object detectors are all just based on clip. Look at this, OpenSeg, clip, BLID, clip. People talk about the importance of open source in machine learning research and generally working in public, and I think that the explosion of papers and research that has come out of the clip model is, testament to that. And I think that it's sad to think that we probably already have a clip 2.0 model, but it's not out there and it's not public, so we can't use it and people can't build on top of it. And you have DETIC, two-stage object detector, OWL VIT, region proposal-based approaches. NERF strives to avoid region proposals by incorporating language embeddings in a dense 3D scale field. So region proposals is basically, usually in these object detectors, especially if they're older, there's kind of multiple parts to the pipeline, and you'll have basically a classification head, and then you'll have a region proposal network. So you have different kind of models, different parts of the model. The region proposal is about finding basically the areas of the box, or the bounding boxes within a 2D image, right? They propose a region of the image. That's one way to think about it, right? Region proposal is the task of proposing which part of the image is the region of interest. And then you'll have a separate part of the model, right? The actual classification head that says, okay, well, in this specific image, what does that What does that correspond to? RadCam and attention-based methods provide a relevancy mapping between 2D images and text. Semantic abstraction. Outputting a 3D relevancy score given a query, right? So because you're using Clip, Clip has created a embedding space upon which images and text can be projected into, which means that you can compare any two embeddings in Clip and get some distance between them, right? There's some metric that you can use to compare the distance between those. So you can get the distance between one piece of text and another piece of text, or one piece of text and images, or images and other images. So that's why Clip is so popular. Distilling 2D features into NERF. NERF has an attractive property of averaging information across multiple views. NERF is 3D, right? It creates a 3D volume that with a field inside of it. And most detection and even models like Clip are limited to 2D. So how do you take all this stuff that's for 2D and put it into a 3D world? Panoptic lifting, embedded semantic information from semantic segmentation networks into 3D. This concept has been applied to segmenting objects with extremely sparse user input scribbles of foreground background masks. Our approach draws inspiration from these works. Distilled feature fields or neural feature fusion fields explore embedding pixel-aligned feature vectors from LSEG or Dino into a NERF. Okay, so you have other work here that's done something similar, but instead, I guess they take the images rendered from different viewpoints, run those through a segmentation model, and then apply the classification label that the segmentation outputs into these specific pixels, right? So distilled feature fields and neural feature fusion fields are basically segmentation model plus NERF in the way that this model LERF is language or Clip or language model plus NERF. Demonstrates a method to distill non-pixel aligned embeddings into 3D without fine-tuning. Incorporating language into 3D has been explored in a wide range of contexts. 3D vision question answering. I don't know if there's an actual benchmark for this. 3D visual question answering. I know there's benchmarks for 2D visual question answering, but I'd be curious if there's benchmarks for 3D visual question answering. There's so many different ways to define a 3D scene, though, that it'd be difficult to have a consistent benchmark for that, right? You could define a 3D field, a 3D scene with NERF. You could define it as a bunch of textures. You could define it as a game, like game engine concept, right? Like game engines have like basically scenes. So there's a lot of different ways to represent a 3D place or space, right? There isn't necessarily great agreement on how to do that yet. LERF is more similar to 3D scene representation in robotics, with which use vision language embeddings to support natural language interaction. Okay, so here are some other works that do something similar. VL Maps, OpenScene, using pre-trained pixel-aligned language encoders. In LERF, we compare against one such encoder, LSEG, in 3D, and find it loses significant expressive capability compared to Clip. Yeah, so I bet you if you go into these particular papers here, 21, 2018. Yeah, so these are slightly older, so they're not going to be as good as Clip 2023. You have Clip fields. NL maps say can. So these sound a little bit more similar to this paper where you have clip embeddings of crops into point clouds using a contrastively supervised field and a classical point cloud fusion respectively. Might be a unpopular opinion, but I feel like point clouds are garbage. I've dealt with them many times before. They're just so annoying and difficult and messy, not clean. I feel like point clouds disappearing would be a good thing for the world, and then we just replace everything with NERFs. On the other hand, NL maps SACAN relies on region proposal networks. These maps are sparser than LERF, and they primarily query clip undetected objects rather than densely. So this is an important point here, right? Where region proposal networks, right? You have some network that gives you a specific region of a 2D image, and you can run clip on just that detected image, right? So you could run clip on just everything that's inside this bounding box here, right? This Waldo sitting in the Twizzlers. Or you could run clip on the entire training image, right? So you can run clip on just a region and get a clip embedding out of that, or you can run clip on the whole image and get a clip embedding out of that. So it sounds like kind of what they're teasing here is that in this paper, in the LERF paper, they're going to be using clip on the whole image, right? The whole rendered view, rather than running clip on a specific region of a rendered view, which is probably what this approach uses. NL maps SACAN. Concept fusion fuses clip features more densely into RGBD point clouds. Objects, okay. LERF does not use region or mask proposals. I just love it when this happens, right? Sometimes over the course of time, research becomes more and more complicated. So sometimes the way that these systems in robotics and in computer vision work, the way to get more performance juice out of them is just to add more bells and whistles. And you'll see the kind of like this kind of like increasing complexity of the systems that are used. But sometimes actually removing some of the bells and whistles actually leads to better performance. And I really love it when that happens. And it seems like that's kind of what happened here, where you have some work where now they kind of added more region and mask proposal, and then LERF was like, actually, wait, let's pare some of that back, and they actually might have gotten better results because of it. I love simple solutions. Yes, there's a bias for simplicity. Brain. LERF contributes a new dense volumetric interface for 3D text queries, improving the resolution and fidelity at which these methods can query the environment when multi-view inputs are available. This is enabled by the smoothing behavior of embedding potentially noisy feature vectors from multiple views to the dense LERF structure. Okay, so that was the related work, which is the section where they basically tell you all the different papers and things that people have done, projects that are related, and how this work, LERF, is different. So now I'm going to present the actual work that they do here in this section here, section 3, Language Embedded Radiance Fields. We kind of skipped this figure, but let's go ahead and look at it. We have 3D scene ramen, and I guess this is the user query eggs, and you can see how it very clearly aligns the eggs, nori, glass of water. This one's a little bit more interesting. This is a hand holding a porcelain hand. So porcelain hand versus fingers. You can see how the clip model, and I mean, this isn't even specific to the NERF, right? Or the LERF. To me, this is really just showcasing how clip is actually quite good, and clip has a slightly different embedding for porcelain hand compared to hand. You have some figurines, cartoon, bath toy, Toy Elephant, Jake from Adventure Time. Apparently Clip has seen enough Adventure Time that it knows who Jake from Adventure Time is. Waldo, Embroidery, the Cookie Bible. This is fucking intense. This is... The Cookie Bible is specific to this book, which is a pretty crazy concept, right? Because you would envision that... Actually here, this is exactly what I would guess. So if you look at this image... If you look at this image, there's stuff in this image that kind of looks like cookies. Like you see this book here, this blue book, has these things here that look like cookies. And then you can tell how the NERF puts, or this kind of like saliency, relevancy map actually has a little bit of detection there, which means that maybe the word cookie is like hitting strongly with that. It's kind of interesting. There's also some accidental or relevancy here, which I don't know what those are. Okay. And then we have shoes, I guess, dress shoes versus Vans and so on. Very cool. Language Embedded Radiance Fields. Given a set of calibrated input images, we ground clip embeddings into a 3D field within NERF. However, querying a clip embedding for a single 3D point is ambiguous, as clip is inherently a embedding and not conducive to pixel-aligned feature extraction. To account for this property, we propose a novel approach that involves learning a field of language embeddings over volumes centered at the sample point. Specifically, the output on this field is the average clip embedding across all training views of image crops containing the specified volume. Okay, so this is the actual target that the neural radiance field is trying to match, right? So the output of the field, where the field is going to be a neural net, and that neural net is going to, for any point in space, it's going to give you the average clip embedding across all training views of the image. So you have some point in space here, you have a bunch of views, right, which are basically 2D images of the same thing. And then each of those 2D images, right, each of those views are going to have some associated clip embedding, which you just get by feeding that into clip. And then for that point, you're probably going to push gradients into that field for all the different clip embeddings, and then the result is that that clip embedding is going to be the average of kind of all the different views. By reframing the query from points to volumes, we can effectively supervise a dense field from coarse crops of input images, which can be rendered in a pixel-aligned manner by conditioning on a given volume scale. Okay, so they're also going to be conditioning on the scale as well. So generally in a NERF, you'll condition on things like the view angle. People have also done research where you condition on like the lighting, or you condition on the weather is something I've seen before as well. Like much like within a diffusion model, there's kind of this guidance weight that allows you to kind of say how much am I going to pay attention to a specific conditioning vector. Maybe there's something similar here. All right, LERF volumetric rendering. So let's get actually into the math here. I don't like how the math is like built into the text. They should have separated it out. But got a NERF takes in a position X, a position in 3D space. This is going to be three-dimensional and a view direction D. It's also going to be another, sometimes two-dimensional because, right, you have roll, pitch, and yaw. So pitch is like this. Yaw is like this. And then roll is like this, right? So sometimes the view directions don't have roll. They only have pitch and yaw. So sometimes they're 2D and sometimes there's 3D. But A NERF outputs the color and the density. Color, density. Something's happening here. Times IRL jumps in. Color is going to be, of course, just 3 numbers. Usually red, green, blue is enough to represent a color. And then density is basically how see-through something is, right? So the way that NERFs are rendered actually is with this thing called ray marching. And for any 2D, for any view, right, you have this 2D image plane, and then you're basically projecting these rays through, and those rays are going to go through your volume of space, and the final color for each pixel on a view, right, the 2D image plane of a view, is basically the accumulated color along that ray. So the density is almost like a weight that is used to make sure that the accumulated color, which is the sum of all the colors that have higher density are going to be the ones that actually contribute the most to the final pixel color value. Samples of these values can be composited along the ray to produce a pixel color. Yeah, so this is basically the ray marching. To create LERF, we augment NERF's outputs with language embeddings. So here you have language embeddings. F lang x s nrd. So f lang is the language model, right? Probably, and it's a function, right? That's what it means here with these parentheses. And the input to this f lang is x vector, x bar here. So this is the actual position. And then s, right? And s is going to be the physical scale, s. So we saw up here conditioning on a given volume scale. That's what this means here, right? So this language model is not only receiving the position, but it's also receiving the scale. And when you give a model additional things like that, it's called conditioning. So this model is conditioned on the scale. If I had to guess, the scale will probably be a number between 0 and 1. And outputs a d-dimensional language embedding. So the output of this function is some embedding, and that embedding has some dimension d, right? So 128, 512, 1024. Usually the dimensionality of these embedding spaces is some multiple of 2, because people like it, kind of like the batch size. Why is the batch size 32 and 64? Well, that's just the way it works, right? Because our computers are based around this binary system. Choose this output to be view independent, since the semantic meaning of a location should be invariant to the viewing angle. This is interesting because I don't necessarily agree with that. I think that the viewing angle is going to change the semantic meaning, right? You could imagine like a poster or something like that. And the front of the poster is going to have some semantic meaning, but the back of the poster isn't going to look like anything. So it's going to have a different semantic meaning. So obviously you don't like this paper works. So they by having this assumption, right, this prior of view independent semantic meaning, they can probably train things a little bit faster, but this could be a work that someone could extend, right? Someone could take and condition this language model on not just the position and the scale, but also the view direction, right? So you have different semantic meaning depending on the view. This allows multiple views to contribute to the same field input, averaging their embeddings together. Scale S represents the side length in a world coordinates of a cube centered at X. Okay. So this is the actual volume. A cube centered at X bar. So NERFs are limited, right? They define a field that is bounded by a specific volume and space. So sometimes there's NERF papers where the NERF is defined by a sphere, but I would say most of them are defined by a cube. So that seems pretty standard. Analogous to how MIP NERF incorporates different scales via integrated position encodings. Yeah, there's different ways to define the position of something, right? So you could imagine if you had this volume here, right? One way to define this red tag here is, I don't know, maybe 0.1, 0.1, 0.1, right? Like a vector that is basically like how far away from the center of this volume is this thing. But there's more clever ways to specify the position of something or of a point in a volume. And this kind of is known as the kind of field of positional encodings. And there's different types of positional encodings that have different advantages. And even within something like a sentence, right? If you're looking at a transformer, which is reading sentences of text or sequences, usually there's a position encoding for specifying where within the sentence that it, or a specific word or a specific token is. So there's a lot of different cool positional encodings that all have different kind of tricks and uses. Rendering color and density from LERF remains exactly the same as NERF. To render language embeddings into an image, we adopt similar technique as prior work. Render language embeddings along a ray. Here's the ray that is being projected from the view and goes through every pixel in the image plane. Since LERF has a field over volumes, not points, we must also define a scale parameter for each position along the ray. We achieve this by fixing an initial scale in the image plane as image and then define S of t to increase proportionally with focal length and sample distance from the ray origin. Okay, so the image plane as image is basically the actual 2D plane that you're kind of basically looking from. So you have some 3D volume in space, and then you're going to be looking at it from a specific angle, and there's going to be some little box basically, right? That box that you look through is going to be the image plane. Maybe I shouldn't be using my hands, but the way that I understand things. Define S of t to increase proportionally with focal length and sample distance. So the focal length is basically the distance from this image plane to the focus, right, which is basically camera geometry. Right? You guys have probably seen this kind of stuff, but see if I can find a good. I feel like this is good. So you have a camera, right, and it's looking at some point, and then the plane here that is aligned with the camera, this is the image plane. The focal length is basically the distance here. If I can find a good camera geometry focal length. Yeah, there you go. So that's the focal length. It's going to roughly be the center here. And you don't need a actual lens to have a focal length, right? Here, the image plane is, it's basically like a virtual camera. Think of it. Sample distance from the ray origin. So this is the where your original point is. S of t equals S image times f xy over t. Okay. So you have here the focal length. T is probably the point or the distance along the ray. And then S image is the image plane. Geometrically, this represents a frustum along the ray, right? Frustum is point triangle. We calculate rendering weights as in NERF. T of t is the integral over t, so the area under the curve of the exponent of negative sigma s ds. Wt equals the integral over t of that function here, this t function, times sigma t dt. Integrate LERF to obtain raw language outputs. So phi hat lang is equal to the integral over all t of wt f lang rt st, right? Where f lang is the language model, rt is the ray, which of course is a function of t, and then s is the the scale, which is also a function of t. And this dt here basically means that you're taking the derivative of that because the integral is also with respect to t. Finally, normalize each embedding to the unit sphere as in clip. Normalize each embedding unit sphere as in clip. So clip is going to create an embedding, and an embedding at the end of the day is just a vector, right? An embedding is basically a vector in a high dimensional space. So you're going to have different vectors with different lengths. It's not necessarily going to be normalized. So you're going to have to take that embedding vector that comes out of clip, normalize it such that it is of unit length, or at least on this unit sphere, right? Find that spherical interpolation between samples on array is unnecessary because non-zero weight samples along array tend to be spatially close, and instead opt for a weighted Euclidean average followed by normalization for implementation simplicity. Okay. So what they're saying here is that they're going to have different clip embedding vectors for each view of a point. And what they're going to do is they're basically just going to weighted Euclidean average, which is just a fancy way of saying they're going to average all of those vectors and then normalize them, the unit sphere. Or implementation simplicity is like the fanciest way of saying because it was the easiest thing to do. All right, let's look at this 2D clip versus LERF. The left visualizes similarity interpolated over a patchwise clip embedding. So I guess this is a clip embedding that is applied over different patches within the image. And the right rendered from LERF. So you have on the left here, this is the patchwise clip embedding, and on the left you have actual LERF. Because volumetric language rendering incorporates information from multiple views, 3D relevancy activation maps have better alignment with the underlying scene geometry. Yeah, I agree with that. I think the only thing they're really showing you here is that LERF uses a NERF, which is a 3D concept, and then here this 2D clip is just using image patches, which are 2D concepts. So 3D is better at 3D than 2D. I don't really know exactly what they're trying to like show here, but it's there. Multi-scale supervision. Supervise language field outputs. Recall their math definition. Flang language field outputs are the outputs of this language function here. Recall that we can only query language embeddings over image patches. Yeah. So you can only feed 2D images into clip. You can't feed 3D anything into clip. Clip takes 2D images, right? So you have to give it a patch, image patches, which is basically just another way of saying a little chunk of the image. Therefore, to supervise the multi-scale LERF, we supervise each rendered frustum with an image crop of size S image, centered at the image pixel where the ray originated. Okay, so they're basically taking a crop of the full image plane, which I think is what we're seeing here, right? So there's some central pixel here, and then they take a crop around that pixel. Practice, recomputing a clip embedding for each ray during LERF optimization would be prohibitively expensive. So instead, we pre-compute an image pyramid over multiple image crop scales. Okay, so what they're saying here is that every pixel in an image like this, when you're doing a NERF, every pixel has a ray. So for every pixel in this training image, there's a ray, right? Let's see if we can get a good example of that. NERF ray per pixel. Yeah, this is the original NERF paper, but for every pixel in this image, right, for every pixel in this image of the truck, right, this particular view, you're going to need a ray. So every single pixel along this 2D image has a specific ray associated with it. So if you had to basically do clip for every single ray, you would be there until like forever, you know, it would just take you forever. So what they're going to do is they're only going to compute clip for a couple different image crop scales. Right, so rather than doing clip for each ray and then rendering something that's centered around that ray and then feeding that into clip, they're basically going to crop 3 things and then only feed those 3 different things into clip. So you basically reduce the total amount of inferences you have to perform with clip. I wonder if, I wonder what clip they use. It'd be interesting if there's someone who's made, because like this, the speed of this training is going to very much depend on how fast you can perform inference on clip, right? So I wonder if someone has taken clip and produced a 4-bit like sparse version of clip that is significantly faster than like a full precision clip. It seems like that would be a way to increase the speed of all of these different algorithms that are based on clip, is to have a clip that is significantly cheaper to perform inference with. This pyramid has n layers sampled between, okay, so even the number of layers is parameterized, it's a hyperparameter, with each crop arranged in a grid with over 50% overlap. During training, we randomly sample ray origins uniformly throughout input views and uniformly randomly select S image. Okay, so you have random sampling of ray origins and random sampling of the scales. Since these images don't necessarily fall in the center of a crop in this image pyramid, we perform trilinear interpolation between the embeddings from the 4 nearest crops for the scale above and below to produce the final ground truth embedding. Okay, so they're doing a little bit more averaging, or in this case, interpolation, which is probably why in all of these examples you see it kind of diffuse out, right? So you see that pretty much in all these examples, the center of the part of the relevant thing is like bright red, and then it kind of red to yellow to green to blue to dark blue, right? So the fact that it kind of diffuses out like that, and I'm using the word diffuses not to confuse with diffusion models, but this kind of stuff to me like screams interpolation and averaging, right? Because all the volume that's like around this area here, the clip embedding, because they were made with the averages, some of the stuff that's unrelated was close enough to this concept that it has a little bit of that clip vector in it, right? We minimize a loss between rendered and ground truth embeddings, which maximizes cosine similarity between the two. This is the metric. So clip produces vectors in an embedding space. To compare how similar vectors are, you can use something like cosine similarity. Scaling by a constant, lambda lang. So L lang is equal to negative lambda lang phi lang times phi lang ground truth. So this is the similarity, I think. Yeah. So this is the dot product here, which is cosine similarity. And this is the language vector 1, and then this is the language vector 2, and then this is basically giving you the cosine similarity between those two language vectors, and then you're multiplying it by this hyperparameter here, negative lambda. Ablations. We ablate dyno regularization and multi-scale training and highlight qualitative degradation and relevancy maps here. LERF without dyno and LERF. Okay, so I think that they're probably going to talk about this soon, but it seems like with this additional dyno regularization, you get a little bit less of that kind of diffusion cloud, kind of like misty artifact, and it becomes a little bit more concentrated. Naively implementing LERF as described produces cohesive results, but the resulting relevancy maps can sometimes be patchy and contain outliers in regions with few or little foreground-background separation. Patchy and contain outliers. This is no longer a math definition. Highlighting. To mitigate this, we train an additional field, fdyno, which outputs a dyno feature at each point. Okay, so much like you had an original neural radiance field that outputs a color and opacity, then you have this language field that outputs an F language, a language vector, or a clip vector, clip embedding for each point. Now you have a third field, third neural net, that outputs a dyno feature. And note how this neural net, the fdyno, is only taking in X, right? So the language field up here was taking X, which is the position, but it's also taking S, which is the scale, right? And the original NERF is taking in the X and it's taking D. And then this one, the third field, the third neural net, is taking only X. Dyno has been shown to exhibit emergent object decomposition properties despite training on no labels. So this just means that the semantic understanding that Dyno has is enough for it to understand that, I don't know, maybe the spoon has a handle and a head or something like that, right? It's object decomposition. Making it a good candidate for grouping language in 3D without relying on labeled data. Because Dyno outputs pixel-aligned features, fdyno does not take in scale as an input, and it is directly supervised for each ray with the Dyno feature it corresponds to. So Dyno outputs pixel-aligned features, fdyno, right? What that means is that Dyno is more like a segmentation model, right? Where it's going to tell you, here you give me an image, and then every pixel in that image, I'm going to tell you the feature that corresponds to that exact pixel, right? So Dyno knows which part of a 2D image corresponds to which feature, which is different from Clip, right? Clip is not pixel specific. Clip takes a whole 2D image and gives you a single embedding vector for that whole 2D image. So that's why Clip, you need to give it the additional scale, condition it on the scale, but something like Dyno, you do not need to do that. we render phi dyno identically to phi lang, except without normalizing to a unit sphere, and supervise it with MSE loss on ground truth dyno features. I wonder why they didn't do that. Huh. I'd be interested to see what the ablation for that is, and what, maybe think deeper about why would normalizing it cause issues. Dyno is used explicitly during inference and only serves as an extra regularizer during training. Clip and dyno output heads share an architectural backbone. Okay. This makes more sense. So if you had 3 different neural nets here, right? If you had your original NERF neural net, which is outputting the color and opacity field, you have your language field neural net, which is outputting clip vectors, and then you have your dyno neural net, which is outputting these dyno embeddings, right? You would have to perform 3 different models, have 3 different models that you're doing inference on at training. But they got lucky here, or not lucky, but as in they designed it in such a way that both clip and dyno share the same backbone, which means that the majority of the inference computation can be shared between clip and dyno, right? You take an image, you feed it through clip, and then you're feeding it through dyno. It's largely basically the same, right? So model backbone versus head. Yeah, so get a good picture here. This isn't like ideal, but it's kind of the same. But like, think about it this way. So the dyno and the clip model share the same backbone. So basically all this stuff here would be the same, and the only thing that's different between dyno and clip is the last stuff here, normally called the head. So in a neural net, the stuff that's at the beginning is usually called the backbone, and then the stuff that's at the top, right at the very last, the final layers, those are called the head. LWAG, language plus swag. Swag lang. Intuitively optimizing a language embedding in 3D should not influence the distribution of density in the underlying scene representation. Capture this inductive bias in LERF by training 2 separate networks, one for feature vectors, the other for standard NERF output. Okay, so actually, it seems like maybe the dyno and the clip fields are not 2 separate networks. So you don't actually have 3 neural nets here. You only have 2. You have one neural net, which is parameterizing the dyno and the clip vectors, and then you have another neural net, which is parameterizing the NERF, or the field, right? Gradients from L lang and L dyno do not affect the NERF outputs. It can be viewed as jointly optimizing a language field in conjunction with a radiance field. Okay, so basically, there's no gradients that are going between. They're training 2 separate things here, right? They're training one network that outputs RGB and density and one network that outputs dyno and clip, which doesn't seem like the case in this picture, right? In this picture, it actually seems like this is one network that is has 4 different kind of heads here that are all pushing gradients into it, but the way that they just described it there, it's 2 separate networks. You have one network that outputs these things here, RGB and density, and then one network that outputs these things here, the dyno features. We represent both fields with a multi-resolution hash grid. This is not quite an octree, but it's something similar. It's basically an efficient way of storing information in a 3D volume of space that is fast from a computation side. We adopt the NERFacto method from NERF Studio as the backbone for our approach, leveraging the same proposal sampling, scene contraction, and appearance embedding. So these are different tricks for NERFs that are part of the NERF studio. So of course they're going to use them, right? If you have them available, why not? Querying LERF. Often language models like CLIP are evaluated on zero-shot classification, where a category is selected from a list guaranteed to include the correct category. Yeah, so this is the difference between open vocabulary detection and closed vocabulary detection, right? In open vocabulary detection, you're just saying what is the word associated with this, but in closed vocabulary, it's more akin to classic classification, at which point you're just saying, is this a cat or a dog? And everything is limited to either cat and dog, as an example. However, in practical usage of LERF on in the wild scenes, an exhaustive list of categories is not available. View the open-endedness and ambiguity of natural language as a benefit. I 100% agree. I feel like we need to get away from these one-hot vectors and these like closed vocabulary sets. Go lean into the fact that language is a rich space that is the result of thousands and thousands of years of humans kind of creating this what is language, right? I don't know. Querying LERF has two parts: obtaining a relevancy score and automatically selecting a scale S. How this is done. To assign each rendered language embedding a score, we compute the clip embedding of the text query, right? So creamer pods would be the text query, and then you can feed just the text creamer pods into clip, and then clip will give you a embedding vector, right? And that's what they have here, by query, along with a set of canonical phrases by I canon. Okay, so what is canonical phrases? There's some kind of like prompt engineering crap here. We compute cosine similarity between the rendered embeddings and the canonical phase embeddings, then compute the pairwise softmax between the rendered embedding text prompts. Okay, so they're taking that text query embedding, and then I don't know what the canonical phrases are. I'm guessing it's just like they just add more crap to it. So like rather than just saying creamer pods, it's like image of creamer pods or something like that. Basically, they add these little extra words to the text query that are kind of like hard-coded, and then by doing that, you get a little bit broader, you know, just so that the clip embedding vector from that text query isn't like, sometimes you can get things that are wrong, right? Like if you say, I don't know, there's like enough ambiguity in the English language that adding this additional kind of like phrases before after might be a good thing. But I don't know what they actually mean by canonical phrases just yet. Compute the cosine similarity between the rendered embeddings and the canonical phrases, and then compute the pairwise softmax between the rendered embedding text prompts. The relevancy score, which is what you're seeing here, right? The color here is the relevancy score, these images, is then basically, this is the dot product, this is the dot product, this is the dot product. You take the exponent of all of those things, and that's basically what the softmax is doing. The softmax here is basically just making that between 0 and 1, right? So softmax function, all it really does is it basically takes an input. This is not softmax. This is softmax. That's not softmax either. This is softmax. So softmax basically takes any input, which can be from negative infinity to infinity, and squashes it into a 0 to 1. And you can, of course, scale it. There's different variables here that you can change so that it goes from -1 to 1 or so on, right? But largely, they want a relevancy score, which is going to be between 0 and 1, but the similarities between these don't necessarily need to be between 0 and 1, so that's why they're putting them through the softmax. Intuitively, the score represents how much closer the rendered embedding is towards the query embedding compared to the canonical embeddings. All renderings use the same canonical phrases: object, things, stuff, texture. We choose these as qualitatively average words for queries users might make, and then found them to be surprisingly robust to queries ranging from incredibly specific to visual or abstract. So this is the canonical phrases that they're referring to here. It's basically the clip embeddings associated with something like object, thing, stuff, or texture. Yeah, choosing these phrases is susceptible to prompt engineering. It's just more hard coding, but hey, you know, like if it works, it works. Fine-tuning them could be an interesting future work. Okay, that's kind of cool. For each query, we compute a scale to evaluate flang. To accomplish this, we generate relevancy maps across a range of scales, 0 to 2 meters with 30 increments. Okay. So this is some hard-coded stuff here, but basically, I'm gonna get out my little blue color for numbers, but they basically choose a couple different scales here, 30 different scales between 0 to 2 meters, and then select the scale that yields the highest relevancy score. So for different scales, you're going to have a different clip vector, right? And that different clip vector is going to either be more aligned with the original prompt or less aligned with the original prompt, right? So they basically scan over these different scales, and whichever scale produces the clip vector that has the highest relevancy score, that's the scale that they choose. So that's roughly like what is how much space kind of the concept takes up in 3D space is coming from that, right? So it's important to note that the scale isn't something that's being predicted. It's not something that the model has learned. It's basically something that the model's been conditioned on, and then you're basically sweeping over all the possible scales and then seeing the one that is the best. So this just seems a little bit intense. Ideally, you wouldn't have to do this. Ideally, you wouldn't have to sweep over all the possible scales and then select the one that yields the highest relevancy. If there was some way to kind of learn the scale or maybe get it from the user or I don't know, find some kind of prior that allows you to not have to do this, I think that would be more optimal, because you're going to have to do this every time you perform inference, which is going to be slow. Regions of the scene that lack sufficiently views, such as those in backgrounds, may generate noisy. We discard samples that were observed by fewer than 5 training views. Okay, so there's some kind of filtering here where they get rid of by fewer than 5 training views. How are they going to know the number of training views associated with a specific sample? I don't know, this seems a little sketch. Localization comparison. Qualitative comparison on localizing long tail objects from novel views. LSEG, OWLVIT, and LERF. This is 3 different techniques. Of course, OWLVIT is 2D. LERF is the 3D one that we're reading here, and then LSEG I think is also another different type of 3D. Cookbooks, olive oil. You can see how LSEG is basically garbage. It predicts things that aren't at all books or olive oil. And then OWLVIT and LERF. LERF is pretty much spot on. Gets the olive oil and the books, and then OWLVIT gets about 50% there. Comparison to LSEG in 3D. LSEG performs well on glass of water since cups are in the COCO dataset, but cannot locate an out of distribution query like an egg, right? So LSEG is not open vocabulary, right? It's using segmentation data, specifically from the COCO. The COCO has a limited set of categories, So anything that is not one of the cocoa categories, such as egg, is going to be basically out of distribution, right? So LSEG works well with things like water, but does not work well with things like egg. Egg is not part of the cocoa categories. We implement NERF in NERF Studio, or LERF in NERF Studio. Top of the NERF facto. Proposal sampling is the same, except we reduce the number of LERF samples from 48 to 24. So this is the number of samples along a vector. So if we go back to this, these dots, each of these dots represents one sample. And for every dot, you have to basically perform inference on your neural net that represents this NERF. So reducing the total amount of dots, the total amount of samples is going to speed up your training, it's going to speed up your inference and so on. So they're going from 48 to 24 samples. We use OpenClip VIT B16 model. So this is the actual clip that they used. It's been trained on the Leon 2B dataset with an image pyramid varying from 0.5 to 0.05, 7 steps. Okay, so here I have the image pyramid here. It looks like there's 3, but the actual number of steps on the pyramid is actually 7. The hash grid used for representing language features is much larger than a typical RGB hash grid. It has 32 layers from a resolution of 16 to 512 with a hash table size of 2 to the 21 and a feature dimension of 8. So this is the structure that they're using to store and access points inside this volume. Clip MLP, so this is the multi-layer perceptron that's part of Clip, the very last, the head, basically. Has 3 hidden layers with width 256 before the final 512 dimension clip output. So this is the dimensionality of the clip output. Right, so crash that. Make sure we get it correct here. 512 dimension clip output. So up here, right, where they said flang XSRD, D is 512. So the language embedding and the image embedding that's going to come out of clip is going to be 512 dimensional. The Dino MLP for FDino has 1 hidden layer of dimension 6. It's Atom Optimizer with all the different tricks here. You have weight decay, you have learning rate scheduling, trained 30,000 steps. Good results can be obtained in as few as 8 minutes. So it's important to note that this here, 8 minutes, this is per scene, right? So one of the kind of most annoying things about NERFs is that you have to train it per scene. So it's 45 minutes to train this bookstore, 45 minutes to train this garden, 45 minutes to train these shoes. So, you know, like they were also saying that it's 45 minutes to collect the data. So it takes 45 minutes to actually collect with your cell phone all that data. I forget exactly where they put it, but we read it earlier in this paper. Yeah, so where is it? Here. Handheld phone capture within 45 minutes. Okay, so record your whole thing. I guess it doesn't take 45 minutes to actually record the whole scene, but maybe 5 minutes to record, walk around your scene with the cell phone, and then 45 minutes to actually train it. Train on an NVIDIA A100 with roughly 20 gigabytes of memory. So you could actually probably run this on a smaller GPU, but you know what? One can interactively query in real time within the NERF Studio viewer. Lambda used in weighing clip loss is 0.01. When computing relevancy score, we compute similarity by 10 as a temperature parameter with a softmax. Okay. So the similarity score, before it is being fed into the softmax, they multiply it by 10. We examine the capabilities of LERF and find that it can effectively process a wide variety of input text queries, encompassing various aspects of natural language specifications that current open vocab detection frameworks encounter difficulty with. So existing 3D scan datasets exist. They tend to be either singular objects or RGBD scans. Select 13 scenes containing a mixture of in the wild and long tail scenes. Captured the scenes using the iPhone app Polycam. Runs onboard SLAM to find camera poses and uses image resolution. So SLAM is simultaneous localization and mapping. That is a robotics concept, and it's the process of simultaneously, which basically just means at the same time, creating a map of your space and then also localizing your camera or yourself within that map. So what does that mean? That means that when you're creating this 3D view here, right, you're walking through it with your cell phone. What SLAM does is it builds this 3D map for you, and then also tells you where the camera was for each individual picture. So there's a lot of different ways to do SLAM. There's things such as ColMap here. It's a common algorithm that's used for this. General purpose structure for motion and multi-view stereo. We visualize relevancy score by normalizing the color map for each query from 50% to maximum relevancy. Extensive visualizations of all scenes can be found. Because of the lack of discrete categories, objects can be relevant to multiple categories. Yeah. Multiple queries, which is what we saw with the cookies, right? We're like cookie-like things, and then also the book that's had the word cookies on it were both had high relevancy to the word cookie. Here we got little precision recall curves for 3D existence experiments. I guess they do have a benchmark for 3D scene understanding. So recall is basically out of all the things you should have detected, how many of them did you actually get? And then precision is how good were you at only getting the things that you should have gotten. They basically trade off kind of how trigger happy you are and then how precise you are. Distance determination. If we evaluate LERF can detect whether an object exists, we label the ground truth existence for 5 scenes. Okay, so somebody actually, this is maybe how they actually did this benchmark, is they had someone sit through and like label specifically which parts of the 3D scene correspond to which objects. Compare against LSEG, but implement in our own code base for apples to apples. We remove scale as a parameter since it outputs pixel-aligned features. We report precision recall. Of course, LSEG, which is not trained with CLIP, instead is trained with COCO segmentation. It's not going to do well natural language and stuff that's outside of the categories of COCO, which is what they've been saying. To evaluate how well LERF can localize text prompts, we render novel views. For 3D methods, we consider the label a success if the highest relevancy pixel lands inside a box. Somebody is labeling bounding boxes for this. LVIT performs LSEG in 3D. I think LVIT does not. It's also trained with clip, so I guess it should also be able to use the kind of like fuzzy matching of natural language. LERF struggles with identifying objects that appear visually similar to the query. Zucchini also activates on other long greenish vegetables, and leaf activates on the green plastic chair. Yeah, so this is the problem with clip, right? Is that the strength of clip is also the weakness of clip, right? Where clip just projects images and text onto the same embedding space, but in that same embedding space, things which might be semantically different to a human might actually be close together in clip space, right? So here, for example, right, there's like a picture. I guess we can just use the example they say, but they have the picture of the grocery store, and the word zucchini in clip embedding space is probably really close to the word cucumber and corn and other things that are like long and green, right? So if since you're using clip and you're using this distance in clip space to basically determine relevancy map, you might not get the kind of like super hardcore like relevancy map that you want, right? You're going to get a little bit fuzziness because everything in this picture is somewhat similar to zucchini. I think they could have maybe like normalized it in order to prevent this, right? Where if everything in the image looks like a zucchini, we'll then just normalize it and spread it out in such a way that only the things which are most like a zucchini light up. No dino. Removing dino results in qualitative deterioration in the smoothness of the boundaries and relevancy maps, especially in regions. Okay, so this makes sense. Dino has kind of pixel level features, so it makes sense that it makes the actual like as they say, the smoothness and the boundaries of the relevancy maps nicer. Ablate multi-scale clip by only training on a fixed scale significantly impairs LERF's ability. So they tried rather than doing kind of this like sweep over different scales, they try only a single scale and it doesn't perform as well. And limitations. LERF has limitations associated with both clip and NERF. Some are visualized in figure 9. Like clip, language queries from LERF often exhibit bag of words behavior. Right, so not read is similar to read. And struggles to capture spatial relationships between objects. LERF can be prone to false positive with queries that appear visually or semantically similar. Zucchinis activate on other similarly shaped vegetables. LERF requires known calibrated camera matrices. So what does that mean? It basically means that to create something like a NERF, you need to know these things here. You need to know the position, the view direction of the camera, which means that for any given image that you're using to train a NERF, you need to know exactly where the camera was, exactly where it was pointed to, and you need to know the camera intrinsics, which is like kind of how much distortion there is, like what the focal length of the camera is like. So that can be limiting, but I would say nowadays with cell phones that have IMUs and accelerometers, and it's probably not as much of a problem, right? Because you can kind of get camera intrinsics and camera extrinsics. Quality of language fields is bottlenecked by the quality of NERF reconstruction. Because of the volumetric input, objects which are near other surfaces without side views can result in their embeddings being blurred or their surroundings. Since no views see the background without the object. In conclusion, present LERF, a novel method for fusing raw clip embeddings into a NERF dense multi-scale fashion without requiring region proposals or fine-tuning. We find that it can support a broad range of natural language queries across diverse real-world scenes, strongly outperforming pixel-aligned LSEG in supporting natural language queries. I mean, I don't know, like, how much of that is just because LSEG doesn't use clip and then this uses clip? I feel like this is really just 90% of the work is clip, which is usually the case for these type of things, right? Like, you know, I was saying it at the beginning of this stream, but to me, it's like clip is really the, it's like these memes with like the holding up the world. Yeah, like, like this is clip is the bottom. It supports any line, meaning it can naturally support improvements to vision language models. Code and dataset will be released after the submission process. Supported in part by equipment grants from NVIDIA. And this is a academic work. Cool. Videos. Convergence speed. 1K, 2K, 30K steps. Okay, so you can see here the difference in training time. So this is just a little bit of training, and then here 30K steps, a lot of training. It actually does pretty good at just even a small amount of training. I would have thought this would have been a lot worse than this one. Regions with more common semantics like blue dish soap and more expansive multi-view coverage converge faster. This is probably why they didn't want to condition the semantic, basically the condition the clip model, the clip NERF on viewpoint. I gave the example of like a poster where the front of the poster and the back of the poster would have different semantic meaning, and that would kind of be a reason why you would want to also condition the language embedding on the view and not just the position. But the fact that multi-view, having multiple views of the same thing led it to converge faster is probably why they didn't do that. It would have just taken too much time to train an individual one. Maximum relevancy scores. I mean, these are like normalized, so it doesn't really matter. Like that number's kind of made up anyways. Clip bag of words. Incomplete geometry can produce unreliable rendered clip embeddings. Geometric separation impacts quality. Queries without much geometric separation can blur between objects in foreground and background. Yeah, so because they're doing this like kind of multi-scale thing, and they're basically saying everything in this region of space is associated with toaster. Right, it's like, and they're doing the average there too. So basically like even things that are like in the real world, there's like these kind of hard boundaries where like everything in this point here is all toaster, but then as soon as you go off of it, it's no longer toaster at all, right? But because they're doing these like averaging of the clip embeddings, then as you move away from the toaster, everything is still toaster, it's just like a little slightly less toaster. Detailed illustration of limitations. Reminder. This is kind of cool. So apparently clip thinks that all citrus fruit is kind of the same, as you can see by limes and lemons kind of all being the same, but it definitely knows the difference between nectarines and lemons. Cool. So that was LERF, Language Embedding Radiance Fields. Pretty cool little paper. Very awesome figures, very awesome demo. I love this page. I love the figures. I love the images. You know, makes me realize that clip is just so important for the computer vision community. And it makes me a little bit sad about what that means for the future. You know, like think about all this research is only possible because of clip. And I don't know if OpenAI will ever release another clip, which is sad. So yeah, definitely check it out. I'm definitely going to be on the lookout for whenever this comes out to NERF Studio, and then we'll see. Maybe we do a little NERF Studio code jam, you know, and we try to do something cool with this. Maybe try to make a NERF of Boo or something like that. Add something cool. But yeah, thanks for listening. Hope this was useful. Sleepy3000, hey mate, need some help. Come over to the Discord. Happy to answer questions there. So yeah, thanks for listening. Hope you guys found that helpful. Let me know if you guys have other papers or other things you want me to review, and yeah, see you guys later.